Hi everyone, this is Mr. Glover. We'll do our first video lesson. Before I do anything though, I do want to say I hope that everybody is doing well at home. I know it's difficult and there's probably a lot of anxieties going on and stir craziness even. So just want to check in and make sure everybody's doing all right, and I hope everybody's doing well. Just a bit of info about these videos. I'm going to try to keep them fairly short, just because that makes it more manageable for you and I in terms of time, and it also will cut down on how much bandwidth is needed to access these for people who don't have a lot of internet access. So having said that, we'll jump right into the notes. Before the break, we talked about how to combine functions graphically, and if you recall, there was a math lab. If you weren't in class, make sure you do 5.1. Basically, you took point by point pieces of a graph and you added the x value or the y value of one graph to the y value of another graph if you were adding, or you subtract the y values of two graphs, or multiplied or divided. And we noticed that multiplication and division can lead to some issues, because multiplying by 0 always equals 0. So if one function was 0, the whole thing is 0. And dividing started to give us asymptotes. So today we're going to kind of do a little bit of a different approach. We're going to talk about how to combine functions using algebra instead of using graphs. So that's the whole topic, combining functions algebraically. Just like we can do with numbers and variables, we can write sums, differences, products, and quotients of functions like f of x and g of x. So we're basically going to be doing algebra with functions. Before we go ahead and do that, we need to kind of go over a little bit of notation stuff. First of all, f plus g, f minus g, f times g, and f divided by g of x. So this is going to be the notation. And what this means is f of x plus g of x. The next one would be f of x minus g of x. Then f times g of x, or f of x times g of x. And then lastly, of course, f of x divided by g of x. Now, this is just, all this does is gives us a little bit of a shorter hand way to write it, and it makes it a little bit more convenient to write it out. So just like numbers or variables, all we need to do to create these functions algebraically is literally to add, subtract, multiply, or divide the functions. So let's actually start with some concrete functions. We've got x squared and we've got 3x minus 5. F of x is the label for x squared and g of x is the label for 3x minus 5. So if we want to actually go in and we actually want to calculate f plus g of x, we first take the shorthand version, write it out. So this means f of x plus g of x. And then we literally just replace f with x squared and g with 3x minus 5. So this equals x squared plus 3x minus 5. And then when we get rid of the brackets, it's x squared plus 3x minus 5. So we're just basically changing labels into functions. F minus g equals f of x minus g of x, which would be x squared minus 3x minus 5. And when you're doing subtraction, you've got to be careful because we're subtracting a negative, so that 5 will become a positive, and this becomes x squared minus 3x plus 5. F times g of x, same idea. This is just f of x times g of x. And this equals x squared times 3x minus 5. So we just have to multiply the brackets. X squared times 3x cubed, and then x squared times negative 5 would be minus 5x squared. Lastly, division. f divided by g of x is going to be f of x divided by g of x. It's going to be x squared divided by 3x minus 5. And that's it. X squared over 3x minus 5. So when you actually have to construct the functions, it's not that bad. You just have to know what the notation means and how to use it. Another thing we're going to do with this is we're going to talk about the domains and the ranges. So the domain and range of new functions are directly related to the domain and range of the original. So when you're doing composite functions or combinations of functions, you need to look for things that can cause issues. Those are going to be things like dividing by 0, having negatives inside a square root. Those right now are pretty much the only issues for us. So we're going to build a function, but we're going to keep in mind that root x gives us a restriction. So f minus g of x is going to equal f of x minus g of x. F of x is root x, and g of x is x minus 3. So this is the square root of x minus x minus 3. Or it's going to be root x minus x plus 3. So that's what the actual equation for the function is. And technically we could write f minus g of x equals root x minus x plus 3. So now let's take a minute and let's think about the domains and ranges of all three of these functions. For f of x was root x. So I'm going to split this into 3. We'll do one for each function. F of x equals root x. If you think about the domain, that's all possible x values. That's going to have some restrictions because can't have negative numbers in there. So x is going to be exclusively greater than or equal to 0. That's our domain. And now you need to know a little bit about what root x looks like. So you can use a graphing calculator or you could use Desmos or something, but a square root of x function, it looks something like this. So if that's what the function looks like, our range is going to be above the x-axis because you can't make a negative with a square root, at least not in our number system. So y also is greater than or equal to 0. Moving on, g of x was equal to x minus 3. And again, we can go ahead and we can graph this. That might give us a bit of a picture as to what the function looks like. X minus 3 has a y-intercept of negative 3 and a slope of 1. So it's literally just a line that looks like this. There's no restrictions on x. We don't have a square root, and we also aren't dividing by anything. So x is going to be greater than or equal to 0. Or sorry, x is going to be all real numbers. And then if you look at the graph, you can make any y value. So y is also all real numbers. Lastly, d of x. And d of x was the function we just made. This is root x minus x plus 3. Now, we're going to graph this. Before we graph this, though, we can figure out our domain. We don't need to see the graph to know what the restrictions are on x. If we go term by term, the 3 isn't going to cause us any issues. Minus x, you can plug any number into that, you'll be fine. But the root x gives us problems, and that's why it's related to the other function. Because root x is part of this, we can't have negatives for x. So I know right off the bat, x is greater than or equal to 0. So now let's go to Desmos, let's graph this thing, and then we have a better idea about our range. So I'm going to open up Desmos here. Well, the function is the square root of x minus x plus 3. Square root of x plus x, or minus x plus 3. We get a function that looks like this. What I'm interested in is the range, and if you zoom way out, it kind of looks like a straight line. But it does have a maximum point, and the maximum point is right here at 3.25. So if we go back to our function, or back to our question rather, I can get this to cooperate with me. If we go back to our question, we now have an upper limit to what the y values are. We know what the range is. It can't be any bigger than 3.25. So we can draw a little sketch in here if we want, just so we have an idea what the graph looks like. But basically it looks like this. And this point right here, that's our max. So our y value has to be less than or equal to 3.25. Again, that's something you're going to have to graph it to know the exact value of. All right, on your own. Using f of x and g of x as above, find an equation for p of x equals f times g of x as well as its domain and range. So we've got the same functions. F of x was equal to root x, and g of x was equal to x minus 3. And we want to find f times g of x. So p of x, we have to build it, equals root x times x minus 3. Technically, we can expand it out even further if we want to. We could expand this out into root x times x minus 3 root x. And if we want to, we can take this even further. We can move the x inside the square root. We can call this the square root of x cubed minus the square root of 9x. Now, right off the bat, even if we go back a step and we kind of look at it right here, we've got square root of x as part of our function. We can't have negatives inside square roots, so our restriction is still going to be that x must be greater than or equal to 0. I know my domain, x is greater than or equal to 0. I don't know what this function looks like quite yet, but I can figure that out with the graph. So let's do that. Let's graph this function. I think it might be, well, we'll graph the middle function. You can graph any form of this and it will look exactly the same. So maybe we'll just do the top because it's easier to input that than it is to input the square root of x cubed. So going back to Desmos. We want to know what this looks like. It's the square root of x times x minus 3. The function looks like this. We can zoom out and it just continues going on. So it's like half of a parabola, but it kind of looks a little wonky at the bottom. It does have a minimum value, and that minimum value is -2. So y is going to be anything bigger than that. So if we go back, we now know what the graph looks like. The graph itself is going to kind of swoop down and then quickly increase. It's going to have a minimum, and we can use that minimum to figure out our range. The range is going to be y is greater than or equal to -2. We have to be really careful when we're creating quotients of functions, as we run into problems with division because it allows us to divide by 0. This will create a non-permissible value. And if you remember back a couple of chapters, a non-permissible value is going to lead to wholes or asymptotes. So non-permissible values which can result in holes or in asymptotes. So given f of x is root x and g of x is x minus 3 squared, find an expression for f divided by g of x. Sketch the function, find its domain and range. So we'll start by building it. F divided by g of x, we'll call it q for quotient. Q of x is f divided by g, so it's going to be f of x divided by g of x. We can then plug root x in for f of x. So this is root x divided by g of x, so divided by x minus 3 all squared. So now, just by looking at this, I think we have an idea what's going to happen. If we could cancel x minus 3 out, we would have a hole, but that's not possible. So we're going to have an asymptote at x minus, or x equals 3. We can draw that in right now because we know it's going to be there. The question becomes, what happens on either side of the asymptote? If we look at our x values, figure out our domain, we've got a square root of x again. That's causing a restriction. So x has to be greater than or equal to 0. We can then look at the denominator, and x can't equal 0. So x can't be 3. So for our domain, x is greater than or equal to 0. However, x also cannot equal 3. For the range, we're going to have to go to Desmos. So let's graph this thing. So this function is going to be root x divided by x minus 3 or squared. It looks like this. So as we knew, there was a vertical asymptote at x equals 3, but then the function rapidly increases on either side of our asymptote. So it looks to me like the range can be anything bigger than 0. We can zoom out to confirm this, and yeah, it keeps going. It keeps going forever. Then the other question becomes, can it equal 0? So we've got to go back to our function about this. Technically, if root x equals root 0, the whole thing is 0, which means at 0, y is 0. So that means our range is that y is either greater than 0 or equal to 0. Y is greater than or equal to 0. And the graph looks like this. We can also take existing functions, break them down to find the smaller functions. So basically what we've done so far is you've been given individual functions and your job has been join them together. Now we're going to be given the combined version and we have to figure out what were the originals. This is where it gets a little bit trickier. So write an explicit expression for 3 different functions, a of x, b of x, and c of x, so that a plus b plus c equals h. Now, it's really easy for us to just take the 3 terms, x squared minus 2x and 3, and literally just call each one of them a, b, and c. But we need x to be a variable in each function, so it gets a little bit trickier. If x has to be a variable in each function, we can still use a equals x squared. But b of x has to be a little bit different. B of x can't just equal 2x. You can get creative here. I'm going to call it 3x though. It's 1 more x than we need, but we can get rid of it by having c of x as 3 minus x. So when you join them together, x squared plus 3x plus 3 minus x, sorry, that should be negative, and that should be positive. Those will add up to x squared minus 2x plus 3. We essentially added an extra x in our b term, and we got rid of it with our c term. We could have done b of x as negative 2x, and we could have done c of x as 3 minus x there's technically infinitely many ways of doing this. Write an explicit expression for two different functions, f of x and g of x, so that h of x is f minus g. So in this case, we want x squared minus 2x plus 3 to equal f of x minus g of x. So you can do this a bunch of different ways as well. What I'm going to do is I'm just going to call f of x x squared. And then g of x needs to be 2x minus 3. And you're probably going, well, why is it positive 2x and why is it minus 3? It's because when I subtract 2x minus 3, it will become negative 2x plus 3. Again, this is not the only answer. There can be many different ways to do this question. On your own, given p of x is x squared minus x minus 6, write the explicit equations for two functions f and g so that p of x equals f times g of x. So we're given an equation, x squared minus x minus 6, and we need to figure out what two functions are multiplied together to create that function. Sounds a lot like we need to factor p of x. If we do that, p of x equals x squared minus x minus 6, which can be written as x minus 3 and x plus 2. We've now figured out what f of x and g of x are. Doesn't matter which one you call f. Let's say the first one is f of x, and let's say the second one is g of x. Those two functions multiplied together will create x squared minus x minus 6. All right, same kind of thing here. We're given a quadratic. We need to factor the quadratic to figure out what f and g are. So x squared minus 2x minus 8, we need to break it up into two factors. We need to multiply to negative 8 and add to minus 2. So I'm gonna say minus 4, x minus 4, and x plus 2. And now, just as before, call one of them f of x, call one of them g of x. And we're done. Lastly, finding a quotient. This is a little bit trickier, and you'll see why in just a minute. The quotient has to equal x minus 4. But we're dividing two functions. And the idea is that when you divide g of x out of f of x, what's left is x minus 4. So let's come up with a strategy. Let's use an idea here. What if we multiply f of x by something, whatever it is, we'll call it f of x times g of x, so that when we divide by g of x, it is canceled. So for example, let's just say g of x is x. We'll go through a little example here. If f of x equals x minus 4 and g of x equals x, that means q of x equals x minus 4 times x. Oops. And q of x is x. And from the surface, it looks like we can just cancel x out, and it will work out to x minus 4. However, we've got a problem. And the problem is that this is not just x equals 4. We have to carry a restriction from the previous line. We had an x in the denominator, so we have a restriction now that x cannot equal 0. That restriction makes this a new function. This is not just x minus 4 anymore. Technically, if we graphed it, it would literally be a straight line with a hole in it. It would look like this. But we would have this gap in the middle. So because of that, we've got to be a little bit creative. We can multiply f of x, or x minus 4 by anything in f of x, but it can't put a restriction in our denominator. So to fix this, and I'm going to cancel this. This is not going to work. Use a denominator with no restrictions. For example, instead of x, let's make g of x, our denominator, x squared plus anything, x squared plus 1. Now, no matter what I put in for x, it can never equal 0. Same thing with our numerator. We'll build the numerator. It's going to be x plus or x minus 4 times x squared plus 1. So when we find the quotient, q of x, it's going to equal x minus 4 times x squared plus 1, all divided by x squared plus 1. It'll still cancel. The x squared plus 1 will still cancel. You'll get x minus 4, but we don't have a restriction anymore. Technically, if we want, we can go ahead and we can expand this out. We can call this x cubed minus 4x squared plus 2x minus 8, all divided by x squared plus 1. And that's as far as we can go. So we did quite a bit today. We talked about what combining functions algebraically looks like. You just use the notation to figure out whether you're multiplying, adding, subtracting, or dividing. You take the functions, substitute them in where f of x and g of x were. We also went backwards where you're given the function and you have to find an f, a g, and maybe h and k of x as well. So I've got some problems for you to try at the bottom here. Because of our circumstance, I'm going to try to reduce the homework load as I can. So I think what I will do is I'm going to change this to odds. So there's a little bit less work. However, if you're finding that you're having trouble with this stuff, it might not be a bad idea to try and do all these anyways. Anyways, that's where I'm going to stop this lesson for now. I'll be posting this to YouTube shortly, and hopefully I can see some of you when we run our AIM class video conference session.